4 billion years ago, a proto-planet slammed into the moon with the force of 1 trillion atomic bombs. Scientists expected it to leave nothing behind. They were wrong. Something enormous is still buried deep in the lunar mantle, a mass 5 times larger than the big island of Hawaii, pulling the crater floor down by more than half a mile. The moon also shakes, threatening future landing sites. Underground caves lurk in silence. Frozen water hides in permanent shadow. And magnetic swirls on the surface point to buried structures no one can explain. If you find this unsettling, subscribe. You will want to stay for everything that follows. We begin. The Apollo astronauts did not just plant flags and collect rocks. They left something behind that would haunt science for the next 50 years. Between 1969 and 1977, 4 seismometers sat on the lunar surface and recorded everything the moon felt. And the moon, it turned out, felt quite a lot. Over those 8 years, the instruments captured more than 13,000 seismic events. Most were minor. Temperature shifts cracked the surface rock. Meteorites struck. None of that was surprising. Scientists expected background noise from a mostly dead world. What they did not expect was motion from deep below. Hundreds of those events came from inside the moon itself. The strongest tremors originated from 700 to over 1,000 kilometers beneath the surface. Consider what that means. The deepest earthquakes on Earth barely reach 700 kilometers. Whatever was shaking on the moon was shaking from regions our planet never touches. This was not a geologically dead world producing the occasional creak. This was systematic interior motion. The timing made it stranger still. These deep tremors did not arrive randomly. They came in patterns, pulsing and repeating in rhythms tied to the gravitational pull of Earth. As our planet tugged the moon through its elliptical orbit, something inside responded. Researchers identified dozens of individual clusters they called nests. Each nest would activate together, go dormant, and activate again on a tidal schedule, like something underground, breathing to the rhythm of Earth's gravity. This is confirmed. The data has been archived and studied for decades. Here is what remains unanswered. The moon was supposed to be geologically inert. Every standard model agreed it had cooled rapidly after its formation 4.5 billion years ago and spent most of its history frozen in silence. So why would a dead world vibrate on a schedule? Why would its interior flex and respond when Earth pulled it? Something deep in that rock was still moving, still responding, still alive in some way the textbooks had never prepared anyone to explain. At the time, scientists noted the findings, filed them, and moved on. There were budgets to defend and rock samples to analyze, and the data was strange but not immediately dangerous. In 1977, when the funding ran out, the seismometers were switched off. That, everyone assumed, was the end of it. The recordings did not disappear. They sat in archives for decades, patient and undisturbed. When researchers eventually returned to those files with modern computing tools and fresh questions, the patterns looked even more organized and persistent than anyone had originally recognized. The deep tremors were rhythmic, structured, repeating over years in ways that spoke of interior processes still underway. A world every model declared frozen was still pulsing from within. But deep tremors were only the beginning of the story. Something else was happening much closer to the surface. Something more violent. And the scientists who eventually examined it would find the moon was not just quietly murmuring underground. In places, it was still rupturing. Among 13,000 seismic events recorded by the Apollo network, a few dozen stood completely apart. These were different in origin, different in character, and far more difficult to explain. They were shallow moonquakes. Unlike the deep tremors that came from 700 kilometers down, these events originated just 20 to 30 kilometers beneath the surface. That is close, that is crust. And they were powerful. The strongest reached magnitude 5.5 on the Richter scale, which on Earth would knock objects off shelves, crack plaster, and send people running for doorways. On the moon, they lasted more than 10 minutes. On Earth, a magnitude 5 quake arrives like a freight train and fades within 30 seconds. The ground rocks and then quiets because water in the crust absorbs the seismic waves, dampening the energy and bringing things back to stillness. The Moon has no water in its crust, no liquid of any kind to absorb the waves. When energy enters the lunar rock, it has nowhere to go. It bounces, echoes, reverberates. The Apollo seismometers watch the ground ring like a struck bell, vibrating without diminishing for quarter-hour stretches. The scientists monitoring those signals reportedly found it unsettling. The question was, what was breaking? The leading explanation, confirmed by decades of subsequent research, is that the Moon is still slowly shrinking. Its interior has been cooling since it formed, and as it contracts, the brittle outer crust wrinkles and buckles. Scientists estimate the Moon's diameter has decreased by roughly 150 feet over the past several 100 million years, which sounds small until you consider what that compression does to billions of square miles of rigid rock. It creates thrust faults, places where one section of crust pushes over another, storing stress that eventually releases in exactly the kind of surface-breaking events the Apollo instruments recorded. But the distribution of those quakes added another layer of mystery. When researchers mapped where the shallow moonquakes clustered, they found a disproportionate concentration in the northern hemisphere, near where the Apollo 15 mission had landed. That region, it would later turn out, was surrounded by ancient buried structures running for hundreds of kilometers beneath the surface. The shallow moonquakes were not random. They were happening where the geology underneath was already unusual. Here is where it gets genuinely alarming. If the Moon is still shrinking, still cracking, still producing 5+ magnitude events at shallow depths, then anyone planning to build a permanent facility there needs to account for it. The Moon is not a stable platform. It is a world in slow, ongoing deformation, and some of those faults are in places that humanity is now targeting for crewed landings. That detail became a serious concern when researchers looked closely at a specific fault system near one of the most strategically important locations on the entire Moon. What they found in January of 2024 did not make the headlines it deserved, but it should have. In January 2024, a team at the Smithsonian's National Air and Space Museum published findings that should have dominated the news cycle for weeks. They had traced one of the most powerful shallow moonquakes from the Apollo's seismic records back to a specific source. The tremor had not come from some random region of the lunar surface. It had originated from a cluster of thrust faults in the Moon's south polar region, the same region where the National Aeronautics and Space Administration plans to land astronauts. This is confirmed. The study, led by planetary scientist Thomas Waters, appeared in the Planetary Science Journal and laid out the case in careful detail. Using slope stability modeling, the team found that many of the sites being considered for the Artemis program's crewed lunar landings are located in terrain that is vulnerable to landslides triggered by seismic shaking. The Moon's south pole, long celebrated for its access to permanently shadowed craters containing water ice, sits on ground that occasionally ruptures. The specific fault the team examined is called the Lee-Lincoln Scarp, a long ridge in the Taurus-Littrow Valley near where the Apollo 17 crew had explored in December 1972. Measurements suggest this fault has been generating magnitude 3 moonquakes for at least 90 million years. It may still be active today. In late 2025, a follow-up study confirmed the fault had repeatedly shifted the terrain in that valley, and that the driving force behind those shifts was ongoing seismic activity connected to the Moon's continued thermal contraction. 90 million years of repeated rupture, still happening now. For future human residents of the Moon, this is not an abstract concern. Structures built on unstable slopes above active fault systems face collapse risks even from moderate shaking. Equipment anchored to the surface could be compromised. Pressurized habitats have tolerances that seismic events can exceed. The shallow moonquakes recorded by Apollo reached 5.5. In a settlement built without accounting for that possibility, a similar event could be catastrophic. There is a deeper issue here that the Smithsonian study forces into the open. For decades, The working assumption in lunar planning was that the moon was geologically inert. That assumption shaped architectural choices, mission designs, and site selection criteria. If the moon is still actively contracting and producing damaging surface quakes, every one of those decisions needs to be re-examined. The moon is not a stable platform. It is a world still adjusting to its own cooling, still wringing stress out of its shrinking interior, still cracking at the surface in ways that pose real hazards to anyone standing on it. What is remarkable is how long this stayed outside the mainstream conversation about human return to the moon. The shaking was always there in the data. Apollo recorded it. The instruments were sensitive enough. The scientists who studied it understood what it meant. But something even stranger had been hiding in those same recordings. Something about the way the moon rang when it shook. Something that pointed toward a hidden interior far more complex than anyone had imagined. When you strike a tuning fork, it vibrates at a single pure frequency and holds that note until the air slowly drains the energy away. It rings. It keeps ringing long after you expected it to stop. The Apollo seismometers heard the moon do exactly that. Every time something struck the lunar surface hard enough to generate seismic waves, the moon rang for hours, not seconds, hours. On Earth, seismic waves decay quickly. Rock is not perfectly elastic, and more importantly, water fills the tiny cracks and pores between mineral grains throughout the crust. That water absorbs energy as the waves pass through, damping the oscillation the same way a wet cloth quiets a vibrating fork. The ground shakes and then settles. The moon has no water in its crust. The rock is ancient, dry, fractured by billions of years of impact bombardment into a loosely packed outer layer called the regolith, which sits atop deeper consolidated rock. When seismic energy enters that structure, it scatters endlessly, bouncing between grain boundaries and fracture surfaces without anything absorbing it. The moon rings and keeps ringing. Scientists who monitored the Apollo instruments described the experience of watching a large impact event as watching the entire moon vibrate like a giant gong for the better part of a day. That ringing was strange, but it also carried information. The way seismic waves travel through a body reveals the structure of its interior. Different materials have different densities, and waves change speed and direction when they cross boundaries between materials. By carefully analyzing the Apollo recordings, researchers could see that the waves were not traveling uniformly through the moon. They were bending, reflecting, arriving at unexpected angles that suggested the interior had distinct layers and dense structures at various depths. The moon was not a simple ball of rock with a small iron core at the center. Something was down there, creating boundaries, deflecting waves, suggesting concentrations of material that had no business existing in a supposedly uniform planetary interior. This is where the Apollo seismic data hit its limit. The 4 instruments were magnificent for their era, but they could not map the deep interior with precision. They could hint at structure without revealing it. They could suggest complexity without explaining it. And in 1977, before anyone had built a full picture of what those hints were pointing toward, the instruments were shut down. The seismic method had taken the investigation as far as it could go. To see what was actually down there, scientists would need an entirely different approach. They would need to stop listening to the moon shake and start feeling how it pulled. They would need to fly 2 spacecraft in perfect formation around the moon for a year and measure changes in the distance between them down to less than the width of a single human hair. That mission would launch in 2011. And what it found would upend everything. In September of 2011, a rocket lifted 2 small spacecraft from Cape Canaveral and sent them on a slow, looping path toward the moon. The journey took months rather than the usual 3 days. Mission controllers wanted to ease the spacecraft gently into lunar orbit, conserving fuel for the meticulous work ahead. The craft were named Ebb and Flow, chosen by a class of 4th grade students from Bozeman, Montana. Officially, the mission was called the Gravity Recovery and Interior Laboratory. It was the most sophisticated lunar detective operation ever conceived. The idea behind it was elegant and almost impossibly demanding in practice. As two spacecraft fly in formation around a body like the Moon, they are constantly pulled and tugged by whatever mass lies beneath them. A mountain causes a slightly stronger pull, accelerating whichever spacecraft is above it and briefly closing the gap between the two. A void or low-density region reduces the pull and allows them to drift fractionally farther apart. If you can measure those distance changes with enough precision, you can map what is below. The required precision was extraordinary. Ebb and flow exchanged radio signals constantly, measuring the distance between them to an accuracy of a few microns. 1 micron is 1/1,000,000th of a meter. The width of a human hair is roughly 70 microns. The instruments were tracking gravitational effects by measuring changes smaller than that. For a year, the twins orbited the Moon at altitudes sometimes barely above the highest mountains, sweeping back and forth, building up a gravitational portrait of the entire world beneath them. The data accumulated in terabytes. The resolution of the final gravity map surpassed anything previously achieved for any body in the planetary system. Features less than 10 miles across left measurable signatures. And those signatures revealed a moon that was nothing like the simple, uniform world everyone had assumed. Ancient structures appeared buried under the crust, stretching for hundreds of miles. The thickness of the lunar crust varied wildly from place to place. Regions where ancient impacts had crushed and compressed the mantle stood out with unmistakable gravitational fingerprints. The moon's interior was layered, fractured, asymmetric, and complicated in ways that defied the existing models. But one feature dwarfed all of this. One discovery sat in the data like a stone in a pond, and when the right researcher finally picked it up and asked the right question, the ripples would reach every corner of planetary science. The mission ended in December of 2012, when both spacecraft were commanded to crash into a mountain near the North Pole, their fuel exhausted. The data they had collected would take years to fully interpret. The most stunning result would not be published for another 7 years. It had been sitting there the entire time, buried in the numbers, waiting. When scientists processed the gravity recovery and interior laboratory data, the Moon's hidden architecture emerged in unprecedented detail. They found mass concentrations buried beneath every major impact basin, dense compressions of the mantle, where ancient collisions had driven material downward and left gravitational footprints that a billion years of erosion had not erased. They found linear intrusions of ancient magma stretching for hundreds of miles through the crust, evidence of a volcanic history far more extensive than the surface implied. They found places where the crust was 60 kilometers thick, and other places where it was essentially gone, scraped away by enormous ancient impacts that had punched nearly through to the mantle. All of this was revelatory. None of it was the most important thing. The most important thing was a gravitational anomaly of staggering proportions, lurking beneath the largest crater in the inner solar system. It appeared in the data as an enormous excess of mass hundreds of miles underground, far heavier than the surrounding rock, pulling downward with a force that had visibly deformed the basin floor above it. At the time of the mission, no one immediately grasped what they were looking at. The gravity map contained thousands of features, and the south polar region was complex. The anomaly was there in the data, but extracting its full significance required combining the gravity measurements with precise topographic information from a different spacecraft, the Lunar Reconnaissance Orbiter, which had been mapping the Moon's surface elevations in parallel. When planetary geophysicist Peter James at Baylor University finally combined those two datasets and ran the analysis, the result was clear and astonishing. The numbers described a mass buried in the Moon's mantle that had no business being there, a mass that nothing in the existing models could explain. Trust signal. The anomaly itself is confirmed by independent datasets. What it consists of remains one of the most contested questions in planetary science. And there was something else the gravity map revealed that made the discovery even more extraordinary. The region below which this mass was hiding was the most ancient and violent wound in the history of our Moon. A crater so large that it covers nearly a quarter of the entire lunar surface, so deep that it exposes rocks from the Moon's lower crust. so old that it predates almost everything else on the surface. The question was not just what was buried there. The question was how, and whether it had any connection to the catastrophe that created the scar above it. To understand that, you first have to understand the wound itself. There is a crater on the moon that you have never seen, not because you lack good enough equipment or because your view is obscured by clouds. You have never seen it because it is permanently hidden from you. It faces the other way. Every second of your life, it has been pointing away from Earth into the darkness beyond. The South Pole Aitken Basin is the largest confirmed impact structure in the inner solar system. It stretches roughly 1,500 miles across the moon's far side, an oval scar so immense that standing at one rim, you could not see the opposite wall even from a very tall mountain. It plunges up to 8 miles deep, far enough that it exposes rock from the moon's lower crust, material that would otherwise be buried forever. It covers nearly a quarter of the entire lunar surface. The impact that created it struck approximately 4.25 billion years ago, when the solar system was less than 300 million years old. The object that hit was enormous. Scientists now believe it was a differentiated body, a proto-planet that had already developed its own distinct internal layers, the way Earth and the Moon themselves had. It had a rocky outer layer and a dense iron-nickel core. When it struck the young Moon, the collision released energy beyond ordinary comprehension. Consider, the atomic bomb dropped on Hiroshima released about 63 trillion joules of energy. The South Pole Aitken impact released roughly equivalent energy to 1 trillion of those bombs. All of that in a single collision. The Moon should, by any intuitive reasoning, have been obliterated. Instead, it survived. The impactor did not. The object that struck the Moon ceased to exist as a coherent body in the first minutes after contact, or so everyone assumed. A study published in 2025 finally pinned the age of this cataclysm to 4.25 billion years with sample-based precision using material returned by China's Chang'e 6 mission. The timing matters enormously for understanding the early history of the inner solar system. It may even challenge the older theory of a concentrated period of heavy bombardment that many models had assumed. But the most consequential thing about this basin is not its age. It is what the collision left behind, because something survived that impact, not the impactor, exactly, but something that came from it, something that settled into the Moon's interior and stayed there for 4 billion years without ever being fully absorbed or expelled. Something with mass on a scale that challenges description. When the gravity recovery and interior laboratory data was finally analyzed correctly, that something showed up in the numbers. In April 2019, planetary geophysicist Peter James at Baylor University published a paper in Geophysical Research Letters that sent quiet shockwaves through the planetary science community. The paper was titled Deep Structure of the Lunar South Pole Aitken Basin. Its central finding was either one of the most extraordinary discoveries in modern planetary science, or a profound challenge to everything understood about how moons and planets evolve, possibly both. Beneath the South Pole Aitken Basin, hundreds of miles below the already ancient crater floor, James and his team had found an anomalous concentration of mass. The excess material had a minimum mass of approximately 2.18 times 10 to the 18th power kilograms. Written out, that is roughly 2 quintillion kilograms of unexpected material. James offered a comparison to help make that number real. Imagine taking a pile of metal 5 times larger than the big island of Hawaii and burying it underground. That is roughly how much unexpected mass the measurements detected. The gravitational pull from this buried mass was so intense that it had dragged the basin floor downward by more than half a mile. The region that should, by the physics of impact craters, sit at a certain elevation was visibly lower because something enormous underground was pulling it down. The effect was measurable. The data was unambiguous. This is confirmed. The mass anomaly is real and has been verified using independent datasets from separate instruments on separate spacecraft. What no one agrees on is what it is. James's team estimated the material extends to depths of more than 300 miles below the surface. At that depth, conventional planetary processes should have sorted dense materials toward the core billions of years ago. Iron sinks, nickel sinks, heavy oxides sink. The fundamental logic of planetary differentiation, the same process that gave Earth its iron core and lighter rock crust, should have driven any dense concentration downward long before now. Yet there it sits, unchanged, unmoved, still pulling the basin floor toward it after 4 billion years. For the scientific community, this created an immediate and uncomfortable question, not just what the mass was made of, but how it was possible that it was still there at all. On Earth, a concentration of dense metal the size of 5 Hawaiis would sink into the mantle over geologic time. On the Moon, it had not. Either the Moon's deep mantle is far more rigid and cool than standard models predicted, effectively locking the mass in place like a fly in amber, or something else is happening in the lunar interior that current physics cannot easily explain. Both possibilities point to a moon fundamentally stranger than the textbooks described. And then came the question of where this mass originally came from. Understanding why the mass is still there requires thinking about what the moon's deep interior is actually like. After the moon formed, its entire outer layer was molten. A global ocean of liquid rock covered the surface to depths of hundreds of miles. As this magma ocean cooled over tens of millions of years, heavier minerals sank and lighter ones floated. The same basic sorting process that operates on any rocky world during its early molten phase. The moon differentiated. Its interior organized itself into layers. Eventually, the deep mantle solidified. Temperatures dropped. Convection, the slow churning motion that moves material around inside a planetary interior, slowed and largely ceased. The moon's interior became rigid, and rigid rock, unlike the flowing material of a still active interior, does not easily allow dense objects to migrate. Think of it like this. If you drop a marble into warm honey, it sinks slowly. If you drop that same marble into cold wax, it freezes in place. The moon's mantle, over billions of years, transitioned from something closer to honey to something closer to cold wax. Dense material that arrived while the wax was still warm might sink toward the core. Dense material that arrived after the wax had stiffened could, in theory, remain suspended where it landed. This is the key to understanding why the mass beneath the South Pole Aitken Basin might still be there. If the moon had cooled enough before the impact, if the deep mantle had already become rigid enough to resist the settling of dense material, then an enormous concentration of metal dispersed into the upper mantle by the collision could remain suspended indefinitely. Computer simulations support this as a physical possibility. They are not proof, but they are consistent with the data. The alternative requires the moon's mantle to have properties significantly different from what standard models predict, either cooler and more rigid than expected throughout its history, or subject to some other stabilizing process that current understanding cannot account for. Both possibilities challenge established planetary science. Both remain genuinely unresolved. Scientists are not being evasive when they say this question is open. The instruments do not yet exist to distinguish between the competing explanations. What they can say is this: whatever the mass is made of, something unusual about the moon's interior has preserved it for 4 billion years. And the most dramatic hypothesis for what it consists of would, if confirmed, mean that buried inside our moon is the remains of another world entirely. Peter, James, and his team did not stop at identifying the mass anomaly. They went further and proposed a specific explanation for what it might be, and that explanation is as dramatic as anything in modern planetary science. The mass beneath the South Pole Aitken Basin may be the dispersed remains of the iron-nickel core of the asteroid that created the basin in the first place. Consider what that means. The object that struck the moon 4.25 billion years ago was large enough and old enough to have developed its own internal structure. It had a rocky outer shell and a dense metallic core at its center, similar to the arrangement found in Earth or Mars. When it collided with the moon at tens of thousands of miles per hour, the outer rocky layers were vaporized, mixed with lunar material, and scattered. But the dense metal core, the heaviest part of the impactor, behaved differently. Computer simulations developed by James's team show that under the right conditions, a sufficiently fast impact into a moon whose mantle had already solidified enough to resist easy penetration could result in the impactor's metallic core being dispersed horizontally into the upper mantle rather than sinking downward, toward the moon's own core. The metal would spread out, fragment, and then freeze in place as the surrounding rock stiffened. This is a scientific hypothesis supported by simulation, not yet confirmed by direct measurement. If it is correct, the implications are staggering. The moon contains the fossilized remnant of an ancient world, a small proto-planet that existed for only a brief period before being destroyed in a collision, is still present inside our satellite, locked into its mantle, preserved by the very rigidity that should have eventually absorbed it. We are not just orbiting a moon. We are orbiting a moon that is itself a kind of tomb. Humanity has never held a piece of material from another differentiated planetary body. The meteorites that reach Earth come mostly from the outer rocky mantles of broken asteroids. A metallic core is something different entirely. If a mission could ever reach the material buried beneath the South Pole Aitken basin, it would be the single most scientifically significant sample ever collected. That mission does not currently exist. No technology on the horizon can drill hundreds of miles into the moon. The mass may be the most important geological feature in the inner solar system, and for now, it is entirely beyond our reach. But there is a second hypothesis for what the mass might be, one that does not require an alien world buried inside our moon, one that is, in some ways, even more revealing about the moon's earliest moments, and the debate between the two is far from settled. The asteroid core theory is dramatic. It is also far from the only answer on the table. At least one other explanation sits quietly in the scientific literature, backed by different chemistry, different numbers, and a very different story about the moon's earliest years. And in some ways, it is just as unsettling. Think back to the moon's birth. 4.5 billion years ago, the entire body was molten, a sphere of churning liquid rock suspended in space. Scientists call this the lunar magma ocean, and it is among the most extraordinary events in our solar system's early history. Slowly, over tens of millions of years, that ocean cooled. Minerals crystallized out of the melt the way sugar solidifies from a cooling syrup. Lighter minerals floated upward, building the crust. Heavier minerals sank toward the interior, settling into distinct layers. That is the standard picture, and most of it holds. The dense oxide hypothesis says the buried mass is a relic of the moon itself, not the remains of a foreign asteroid. A concentration of extremely dense oxide minerals formed in the final stages of magma ocean crystallization. When molten rock cools slowly, the last minerals to crystallize tend to be the heaviest and the strangest. Chief among them is ilmenite, an iron-titanium oxide that forms in iron-rich melts under very specific temperature conditions. It is genuinely dense enough, in large quantities, to leave the gravitational footprint scientists detected beneath the South Pole Aitken basin. Here is where the theory becomes interesting. As the magma ocean finished solidifying, a thick layer of ilmenite and related oxides would have crystallized just above the core mantle boundary. Gravitational models suggest this layer became unstable, too heavy to remain in place, and eventually descended through the mantle in massive, slow blobs. Most of it would have reached the deep interior. Some of it, however, could have pooled and stalled in regions of the mantle where conditions slowed its descent. Beneath the South Pole Aitken basin, the mantle was transformed by the impact itself. Hundreds of kilometers of crust were stripped away in an instant. The rock beneath was heated, churned, and restructured. Could that ancient upheaval have created exactly the conditions needed to trap a concentration of dense oxides? Could the scar on the surface be the reason for the anomaly beneath it? This hypothesis is scientifically rigorous. It fits the gravity data. Under this scenario, the buried mass is a product of the moon's own formation chemistry, a a frozen relic of processes that ended 4 billion years ago and left their signature locked into the mantle like a fingerprint. That would make the mass a record of planetary birth, not planetary destruction. The problem is the coincidence. Why would the densest concentration of oxide material in the entire lunar mantle sit directly beneath the largest impact crater in the solar system? The two events are separated by hundreds of millions of years. One formed when the moon solidified, the other formed when a massive asteroid struck. That they should overlap at the same location is possible but uncomfortable. Neither hypothesis is disproven. Neither is confirmed. Both require assumptions that cannot currently be tested. Scientists can model the crystallization. They can simulate the impact. They cannot reach into the mantle and tell the two scenarios apart. That gap between data and answer is the frustrating engine driving modern lunar science forward. But what happened next pulled the science out of the laboratory and into a room where very different questions were being asked. For most of its history, lunar science lived quietly in the background. The moon had been visited, sampled, and written up. Funding was modest. The debates were real, but the audience was small, mostly researchers in university departments who followed the journals and attended the same annual conferences. Then the numbers from the gravity map arrived, and the moon stopped being just a scientific question. In December 2023, the United States House of Representatives convened an oversight hearing on mineral supply chains and the new space race. The title alone would have seemed peculiar a decade earlier. Among the witnesses called to testify was a policy expert who cited the buried anomaly in detail, describing the mass and what it might represent if the metallic core hypothesis turned out to be correct. Congress was paying attention. The argument was stripped down and direct. If the mass beneath the South Pole Aitken basin consists of dispersed iron and nickel from an ancient asteroid core, it may represent one of the largest concentrations of those metals anywhere in the inner solar system. Iron and nickel are industrial essentials. They are also increasingly strategic in a world where geopolitical competition over critical mineral resources is intensifying. The moon exists as politically neutral territory, governed by treaties that no nation has yet managed to convert into genuine sovereign property. The hearing was politics, not science, but it was the first moment the discovery moved from laboratory to legislature, from gravity data to national interest. That shift matters. The reaction from the scientific community was divided. Some researchers welcomed the attention, reasoning that political interest becomes funding and funding becomes missions. If Congress cared about what was buried under the moon, perhaps the resources would follow to actually send instruments and find out. Others were uneasy. Economic framing distorts scientific priorities. The goal of understanding the moon's interior becomes entangled when investors and committee members start asking about extraction timelines. That tension has no clean resolution. Space resources occupy genuinely murky legal territory. The Outer Space Treaty of 1967 prohibits national sovereignty over celestial bodies, but it says nothing clear about private extraction. Several countries, including the United States and Luxembourg, have passed domestic laws asserting that their citizens and corporations may legally own materials they mine from space. No binding international agreement exists. The question of who owns what lies buried inside the moon has never been formally adjudicated because until recently, nobody had reason to ask. Into that ambiguity walks the discovery of a potentially enormous buried metallic mass. The science that began with two small spacecraft measuring gravity changes smaller than a human hair now intersects with industrial policy, corporate investment, and the geopolitics of a new era beyond Earth. There is something almost vertiginous about that trajectory. A team of planetary scientists in Texas analyzed archived data from a mission that ended in 2012, detected a gravitational whisper from hundreds of kilometers below the lunar surface, and inadvertently handed legislators an argument in a competition for resources that is only beginning. For the scientists, none of that changes the fundamental question. Whatever the mass consists of, it is real, it is enormous, and it is poorly understood. The path to understanding it runs through rigorous evidence. And some of that evidence, it turned out, pointed in a direction the believers in a single buried object had not fully considered. Not every planetary scientist accepted the dominant interpretation. That matters. Science does not advance by consensus alone. It advances through challenge, through the people in the back of the room who raise their hands and say the model does not hold. The case for skepticism begins with the nature of the measurement itself. The Gravity Recovery and Interior Laboratory mission measured gravity. It did not measure composition. It did not drill a hole. It did not collect a sample. It detected tiny changes in the distance between two spacecraft as they orbited the moon, and from those changes, scientists inferred what lies below. The inference is elegant, but elegance is not proof. Several planetary scientists have argued publicly that the gravity anomaly beneath the South Pole Aitken basin may not require a single massive buried object to explain it. The basin is geologically complex. Multiple layers of impact melt, fractured crust, uplifted mantle, and volcanic intrusion have accumulated and shifted over 4 billion years. Separating the gravitational signature of a buried metallic mass from the combined effects of all those overlapping features requires assumptions about density, depth, and structure that may not hold at every layer. A dense concentration of ordinary silicate rock, arranged in the right configuration, could, in theory, produce a similar gravity signal without requiring an alien asteroid core. The difference between those two scenarios matters enormously for understanding what happened during the early solar system. Yet the data, as collected, cannot currently distinguish between them. The critics are not dismissing the discovery. They are applying the standard rules of scientific evidence. Extraordinary claims require extraordinary evidence, and the evidence in hand remains indirect. One researcher described it plainly. The gravity anomaly tells us where the mass is and approximately how much of it there is. It does not tell us what the mass is made of. Every conclusion about composition rests on modeling assumptions, and modeling assumptions can be wrong. Consider what a gravity measurement actually captures. Two small spacecraft drift in formation around the moon. As they pass over a dense region, the leading craft accelerates slightly. The difference in separation, measured in fractions of the width of a human hair, is converted by mathematics into a density map of the deep interior. That conversion is precise, but it rests on equations that assume certain things about how lunar rock behaves under pressure and how ancient impacts redistributed material. Adjust any of those assumptions and the picture shifts. This is exactly the kind of debate that makes science work. When two teams reach different conclusions from the same data, the field does not simply vote on which answer it prefers. It designs new observations, proposes new missions, and tests each model against every scrap of new evidence that arrives. The process is slow, sometimes frustrating, and occasionally definitive. The skeptical position has not weakened the original discovery. If anything, the ongoing debate has sharpened the questions. The buried mass is real. Its gravitational pull is real. The basin floor really is depressed by the weight of something enormous below it. What remains genuinely contested is the interpretation, the story that explains why the mass is there, what it consists of, and how it has remained suspended in the mantle for 4 billion years. There is something strangely hopeful in that uncertainty. It means the moon still has genuine surprises to offer, answers that future instruments may actually deliver. The question is alive, but the debate also points to a deeper problem in planetary science. One that goes beyond this particular discovery, one that shapes everything scientists can and cannot know about the worlds around us. Here is the uncomfortable truth at the center of planetary science. We cannot see the inside of the moon. We have never seen it. Every piece of knowledge about the lunar interior comes from indirect evidence, from seismic waves that bounce and refract through hidden layers, from gravity fields that hint at density variations far below, from the composition of surface rocks that record ancient mantle chemistry. Every conclusion rests on a chain of inference, and every link in that chain is a model built on assumptions. This is not a criticism. It is the nature of the field. Scientists studying Earth's interior face the same constraints. The deepest borehole ever drilled on our planet barely scratched the crust before being abandoned. Everything known about the Earth's molten outer core and solid inner core comes from seismology, from the way earthquake waves travel through material no human has ever touched. The Moon presents an even steeper challenge. The Apollo seismometers ran for only 8 years before being switched off in 1977. No seismometers currently operate on the far side of the Moon, which is precisely where the most geologically extraordinary features lie. The gravity data from the Gravity Recovery and Interior Laboratory mission is extraordinarily precise but still tells scientists only where the mass is concentrated, not what that mass consists of. The topographic maps from the Lunar Reconnaissance Orbiter are detailed and beautiful, but they show only the surface. Every layer of the interpretation rests on the layer below it. The mass beneath the South Pole Aitken Basin is inferred from gravity measurements. The depth of that mass is inferred from modeling. The composition of that mass is inferred from analogy with other planetary bodies and from simulations of ancient impacts. Each inference carries uncertainty. When the uncertainties stack, the picture blurs. This is why the two competing hypotheses, asteroid core or primordial oxide concentration, remain genuinely unresolved after years of debate. Both are consistent with the available data. Both produce gravity models that match the observations. Both have support in laboratory experiments and computer simulations. Neither can be eliminated without data that does not yet exist. Scientists are not confused or incompetent. They are working at the absolute edge of what current instruments can measure on a question so fundamental that answering it incorrectly would be worse than leaving it open. The integrity of the field depends on that caution. There is intellectual courage in admitting the limits of what a measurement reveals, even when that measurement made headlines around the world. This tension is the permanent condition of any field where the objects of study are unreachable. Astronomers mapping the interiors of distant stars face it. Geophysicists modeling Earth's deep mantle face it. The best minds in the field work with the data available, build the most defensible models possible, and wait for new instruments to close the gap between inference and knowledge. But there is a real cost. The question at the heart of this story, what is actually buried beneath the largest crater in the solar system, may not be answerable in the near future, possibly not in this generation. The gap between what gravity data can reveal and what a physical sample would confirm is vast. And the path across that gap runs through engineering challenges that humankind has not yet solved. The only way to truly resolve the debate is to collect samples from the mantle beneath the basin itself. And that is where this investigation runs into a wall that no telescope or satellite can breach. What waits on the other side of that wall is the most sobering frontier in planetary science. The deepest hole humans have ever drilled into the Earth is called the Kola Super Deep Borehole. It sits in the far northwest of Russia, near the Norwegian border, and it took Soviet scientists 24 years to create. They began drilling in 1970 and reached a final depth of just over 12 kilometers before heat and pressure made further progress impossible. The rocks at the bottom of that hole were expected to be dry basalt. They turned out to be saturated with water, surrounded by hydrogen gas, and so hot that the drill bits failed repeatedly. 12 kilometers, that is the entire depth of human direct access to the Earth's interior. The mass beneath the South Pole Aitken Basin lies hundreds of kilometers down, at minimum 300 kilometers, possibly deeper. The crust above it is itself tens of kilometers thick in places. To reach the anomaly with a physical sample would require drilling through material 25 times deeper than humanity's greatest borehole. In the low gravity and extreme temperature swings of the lunar surface, with no repair crews and no possibility of resupply, no technology to accomplish this exists. No technology to accomplish this is being developed. The engineering challenges are not merely difficult, they are so far beyond current capability that most scientists do not spend significant time thinking about them. The buried mass is, in a practical sense, inaccessible. This is a genuine and largely unacknowledged frustration in the field. Planetary science has spent decades building instruments sensitive enough to detect features hundreds of kilometers underground. It has succeeded spectacularly. The GRAIL mission found something enormous. The question is answered in one sense and completely unanswered in another. There are partial approaches. Future seismometer networks on the Moon could map the anomaly in far greater detail, pinpointing its boundaries and potentially revealing something about its elastic properties, which differ between metal and silicate rock. Improved gravity mapping could tighten the estimates of its mass and distribution. Sample return missions to the South Pole Aitken Basin surface could retrieve rocks that originated deeper in the mantle and were excavated by the ancient impact, giving scientists indirect chemical clues about what lies below. China's Chang'e 6 mission already took a step in that direction, returning the first samples from the lunar far side in 2024. Researchers found them chemically depleted, cold in origin, and geologically distinct from anything retrieved before. The analysis confirmed the far side mantle is genuinely different from the near side, cooler and more depleted in the heat-generating elements that drove volcanic activity. Those samples opened new windows. They did not look directly through this one. The mass remains hidden. The debate continues without the one piece of evidence that would settle it, and it is worth pausing on what that means for how humanity relates to the world closest to it in space. We have visited the Moon. We have stood on its surface. We have brought its rocks back to our laboratories and analyzed them down to the atomic level. And yet the most dramatic discovery in the history of lunar science, an anomalous mass large enough to reshape the basin floor above it, remains fundamentally unexplained after years of study. The Moon is not transparent. Its silence on this question is complete. While scientists debate what is buried hundreds of kilometers down, another discovery was quietly approaching, far closer to the surface. Something entirely different was waiting just below the Moon's skin, and it had been there the whole time. In the summer of 2024, a paper appeared in a leading astronomy journal and immediately became one of the most discussed lunar discoveries in decades. It confirmed something scientists had theorized since the 1970s, something so significant for the future of human exploration that its implications are still being absorbed. A cave exists beneath the Moon's surface, accessible, real, confirmed by radar. The story begins with a pit. The Mare Tranquillitatis pit was first photographed in 2009 by the Japanese Kaguya spacecraft, a roughly circular hole in the dark volcanic plains of the Sea of Tranquility, approximately 100 meters across, with near vertical walls dropping into shadow. Scientists suspected it was a collapsed section of a lava tube ceiling, a skylight into an underground tunnel. Suspicion is not evidence. For 15 years, that is all it remained. Then, a research team at the University of Trento in Italy reanalyzed radar data originally collected in 2010 by the Mini-RF instrument aboard the Lunar Reconnaissance Orbiter. They applied more sophisticated signal processing techniques than had been available when the data was first gathered. What the radar returns showed was unambiguous. Below the pit, at a depth between 130 and 170 meters, a subsurface void extended outward from the shaft. The cave conduit measured at least 45 meters wide and between 30 and 80 meters long. This is a confirmed result. The cave is real. For the first time in history, humanity has direct evidence of an accessible underground space on another world. The significance is difficult to overstate. A cave on the Moon is a shelter. The lunar surface is hostile in ways that require constant engineering solutions. Cosmic radiation streams through the thin void of space and hits the unprotected surface continuously, delivering doses that would be dangerous for long-term human exposure. Micrometeorites, tiny fragments of rock traveling at tremendous velocity, pepper the surface without an atmosphere to burn them up, and the temperature swings are violent beyond anything on Earth. Inside a cave, protected by meters of solid rock overhead, all three of those threats are dramatically reduced. Radiation is blocked, micrometeorites cannot penetrate. And temperature, as instruments have confirmed, stabilizes in ways that the exposed surface never achieves. The pit in the Sea of Tranquility is 375 kilometers northeast of the Apollo 11 landing site, where the first humans to walk on the moon stepped onto the surface in 1969. For more than half a century, that cave waited beneath a world humanity had visited and left, undetected, patient. The radar data that eventually revealed it had been collected in 2010. The cave was hiding in plain sight inside a dataset that sat on servers for 14 years before someone asked the right question with the right tools. Scientists now believe it is almost certainly connected to a much larger system of underground tunnels. The pit is a skylight, a place where the ceiling failed and exposed what lies beneath. What stretches behind it, through darkness that has persisted for billions of years, may be something far grander than the confirmed conduit. The full extent of that underground world has only just come into focus. The cave beneath the Sea of Tranquility is almost certainly not alone. It is a window into a vast and mostly unmapped underground world, created long ago by processes that operated on a scale the moon's quiet surface gives no indication of. Lava tubes form when molten rock flows across a landscape, and the outer surface of the flow cools and solidifies while the interior remains liquid. The liquid drains away, leaving a hollow tunnel behind. On Earth, these structures exist across volcanic regions from Hawaii to the Canary Islands to Iceland. They are scientifically fascinating and occasionally large enough for hikers to explore. The biggest terrestrial lava tubes reach perhaps 30 meters in width before their own weight and Earth's gravity cause the ceiling to collapse. On the Moon, gravity is 1/6 as strong as on Earth. That single difference changes everything. A lava tube ceiling that would collapse under its own weight on Earth can remain stable at far greater widths on the Moon, because the rock above it weighs far less. Theoretical calculations suggest lunar lava tubes could be structurally intact at widths of hundreds of meters, possibly approaching a kilometer, and lengths stretching for many kilometers across the ancient volcanic Maria. The confirmed cave beneath the Mare Tranquillitatis pit, just 45 meters wide in the detected conduit, is likely a fragment of a much larger tunnel. It is a skylight, a place where the ceiling failed and left an opening, offering a glimpse into a system that extends far beyond what the radar captured. How far? Scientists currently do not know. The radar instrument that detected the cave was not designed for this specific task, and its resolution limits what can be confirmed. What is known is that many such pits have been identified across the Moon's surface. Researchers have catalogued over 200 of them, scattered across the volcanic plains. Each one is potentially a skylight into its own cave system. Each cave system is potentially a connected network of underground space that has been sealed and stable since the volcanic activity that created it died out between 1 and 3 billion years ago. For future explorers, the implications are concrete. Building a pressurized habitat on the lunar surface requires shielding against radiation, protection against micrometeorite impacts, and insulation against temperature extremes. Those are solvable engineering problems, but they are expensive and complex ones. A lava tube solves all three at once, and it solves them for free, using rock that has been in place for 1 billion years. An inflatable habitat deployed inside a lunar cave would be shielded from cosmic radiation by solid rock above it. It would be protected from micrometeorites. It would exist inside an environment where temperature does not swing by 300 degrees between day and night. The structure required would be a fraction of the mass and complexity of anything designed to survive on the exposed surface. There is a strange satisfaction in the realization that the same ancient volcanism that built the Moon's dark plains and hid a mass anomaly in its mantle also quietly prepared underground shelters for a species that would not arrive for another 3 billion years. The cave is a gift the Moon has been holding for billions of years, waiting patiently for someone to find the door. But there is another feature of these underground spaces that makes them even more valuable. Something about the conditions inside that no engineer could have designed better if they tried. The lunar surface is one of the most hostile thermal environments in the inner solar system. During the 2-week lunar day, the temperature climbs to 127 degrees Celsius, hot enough to boil water with ease, hot enough to soften certain metals. During the 2-week lunar night, it plunges to 173 degrees below zero, cold enough to freeze oxygen, cold enough to make steel, brittle, and electronics fail without careful heating systems. That swing of 300 degrees occurs in a predictable cycle, and every piece of hardware sent to the moon must be designed to survive both extremes or be kept operating continuously to generate internal heat. The caves change that equation entirely. Data from the Diviner Lunar Radiometer experiment, an instrument aboard the Lunar Reconnaissance Orbiter, revealed something remarkable when scientists examined the thermal environment of the lunar pits. The interior of the Mare Tranquillitatis pit maintains a stable temperature of approximately 17 degrees Celsius. Not in parts of it. Consistently, across measurements taken at different orbital passes, under different lighting conditions, at different times in the lunar cycle. 17 degrees Celsius. That is a comfortable room temperature by any human standard. Shirt sleeve weather. The kind of temperature in which electronics work reliably. Humans can function without extensive thermal gear, and equipment built for standard operating ranges does not require modification. The rock overhead acts as a thermal buffer. The moon's surface heats and cools because it directly receives radiation from the star and radiates heat back into the vacuum of space. Cut off from that direct exposure by meters of solid rock, the underground environment reaches a thermal equilibrium that changes only on geological timescales. The cave does not know whether it is day or night on the surface above it. It simply holds steady. This is not a minor engineering convenience. Thermal regulation is one of the most expensive and technically challenging aspects of designing long-duration lunar habitats. Every current proposal for a surface base includes massive insulation layers, reflective coatings, electric heaters for the cold periods, and radiators for the hot periods. All of that infrastructure adds mass, cost, and failure points to a mission that already operates on the edge of what is technically achievable. A cave eliminates the thermal problem outright. The structure that explorers would need to build inside it is dramatically simpler than anything that would survive on the exposed surface. A pressurized inflatable module designed to operate at a stable 17 degrees requires none of the extreme engineering demanded by the surface environment. The cave does the hard work. There is something worth sitting with in that number, 17 degrees. The same temperature at which humans are comfortable without heavy clothing, at which most standard electronics operate within their rated ranges, at which growing plants indoors is entirely feasible. The moon, which looks so aggressively alien from the outside, is hiding the conditions of a moderate afternoon somewhere inside it. Combined with radiation shielding, micrometeorite protection, and confirmed accessibility through the pit entrance, the underground environment offers conditions that align almost perfectly with what a permanent human outpost would need. Scientists who study lunar exploration logistics describe it plainly. The cave beneath the Sea of Tranquility is the most promising natural site for a lunar base yet identified. But even the cave, with all its advantages, sits above another layer of the moon's hidden world, one locked in permanent darkness and extreme cold, one that holds something far more valuable than shelter. The moon tilts almost not at all. Earth leans on its axis by 23.5 degrees, enough to create seasons, enough to swing the temperature of the Arctic from bitter winter to the midnight of summer. The moon tilts by just 1.5 degrees. That nearly perfect uprightness has a consequence that took scientists decades to fully appreciate. At the moon's poles, the geometry of that minimal tilt means the star at the center of our solar system never rises high above the horizon. It grazes the rims of craters, illuminates the tops of ridges, and never dips low enough to reach the floors of the deepest polar basins. Some of those crater floors have been in continuous shadow for billions of years. No direct light has ever touched them. No warmth has ever reached them. They are, in thermal terms, the coldest stable environments in the inner solar system. The temperature at the floor of a permanently shadowed polar crater drops to approximately 230 degrees below 0 Celsius. At that temperature, volatile molecules cannot escape. Water vapor, carbon dioxide, hydrogen, methane. Any molecule that arrives by impact or migration cannot evaporate. It freezes and stays frozen. Over billions of years, the Moon has been struck by countless comets and asteroids, many of them carrying frozen water and other volatiles. Most of what they delivered to the sunlit surface was immediately lost, vaporized by the heat and scattered into space by radiation pressure. But any volatile material that migrated toward the poles and drifted into the permanent shadow of a crater was trapped. Scientists call these regions cold traps, and they theorized for decades that frozen water must be accumulating inside them. The logic was airtight. Comets and water-bearing asteroids have been striking the Moon for 4 billion years. Some of that water must have migrated toward the poles. Any molecule that wandered into the permanent shadow of a deep crater would be frozen instantly and would never escape. The cold trap collects and holds. The problem was confirmation. Detecting ice inside a crater floor that never receives light from a spacecraft in orbit hundreds of kilometers above is technically difficult. The surface in those shadows is invisible to optical cameras. Radar can penetrate, but interpreting the returns requires knowing the surface texture and composition well enough to separate the signature of ice from the signature of cold, dry rock. Infrared instruments detect heat, and the floors of permanently shadowed craters emit almost none. For years, the evidence was suggestive, then promising, then compelling, and always disputed. The debate had been running for more than 30 years when the technology finally arrived that could settle it, an impactor, a real-time measurement of what the Moon had been hiding in the dark. Then came the moment when suggestion became certainty. A plume of vapor rose from the bottom of a permanently shadowed crater, captured in real time by instruments designed specifically to catch it. The debate did not end completely with that detection, but it shifted irrevocably, from whether ice exists on the Moon to where exactly it lies, how much of it there is, and what it will take to reach it. The implications of that shift extend far beyond the science of planetary geology. They reach directly into the economics of everything humanity might one day attempt beyond Earth. On October 9, 2009, a rocket body traveling at roughly 2 kilometers per second struck the floor of Cabeus crater near the lunar south pole and exploded into a plume of rock, dust, and vapor. This was not an accident, it was a mission. The Lunar Crater Observation and Sensing Satellite carried a trailing spacecraft that flew through the rising plume 4 minutes after the impact and analyzed what it contained. Spectrometers scanned the vapor cloud as the trailing craft descended. The instruments recorded the molecular fingerprints of what had been sitting frozen in that crater floor for hundreds of millions of years. Water, confirmed. Water vapor at a concentration of approximately 5.5% by weight. The mission recovered the equivalent of roughly 100 kilograms of water from a single impact plume. The Moon was not dry, it was frozen. That confirmation, coming after decades of speculation and preliminary detections, changed the trajectory of lunar science overnight. A world that planetary scientists had categorized as a dry, airless, geologically inert rock was suddenly something else. A reservoir, potentially holding enormous volumes of frozen water locked in permanent darkness across multiple crater floors. Since that detection, the picture has grown more complex and more interesting. Studies using radar instruments aboard the Lunar Reconnaissance Orbiter confirmed ice deposits in permanently shadowed regions at both poles. A study released in 2024 found the ice in the southern polar region was more widespread than previously estimated, extending across a larger area and potentially reaching greater depths. More surprisingly, Japanese scientists analyzing data from their own lunar orbiter detected signatures consistent with water ice particles at mid-latitudes and even near the equatorial regions, locations that had never been considered cold enough to hold ice. That last finding, still being evaluated, suggests water may be actively migrating across the lunar surface today. Molecules delivered by micrometeorite impacts or solar wind interactions may be hopping across the surface in tiny jumps, gradually drifting toward the poles and settling into the cold traps. a slow planetary scale process that has been operating continuously for billions of years. The strategic implications are immense. Water can be split into hydrogen and oxygen, the two components of rocket propellant. A base at the lunar poles with access to ice could theoretically produce its own fuel, turning the moon into a resupply point for missions heading farther into the solar system. It could provide drinking water, support agriculture in pressurized habitats, and serve as radiation shielding when packed around a habitat's walls. Water is the single most valuable resource for sustained human presence beyond Earth, and the moon may have it in meaningful quantities. The exact amount remains unknown. The planned rover mission designed to prospect for ice in the South Polar region was cancelled before it could fly. The unanswered questions are enormous. But the core fact is settled. Frozen water is present on the moon, and anyone planning to build a permanent presence there will need to understand it completely. What remains to be explored pushes deeper still into questions about the moon's magnetic history, its volcanic past, and the painted mysteries left on its surface by forces no one has yet fully explained. Ice is not just ice when you are 239,000 miles from the nearest supply depot. That frozen water sitting in perpetual darkness at the moon's poles is something far more significant than a geological curiosity. It might be the key that unlocks the entire solar system. Water breaks apart into two familiar elements, hydrogen and oxygen. Those same two elements, when liquefied and ignited together, produce the most efficient rocket propellant humanity has ever used. The main engines of the space shuttle ran on them. The Apollo program burned a close variant. Every major deep space mission currently on the drawing board needs enormous quantities of propellant, and every kilogram hauled up from Earth's surface costs tens of thousands of dollars to reach orbit. If you could manufacture propellant on the moon, you would never need to launch it from Earth again. A base at the lunar poles could mine ice from the shadowed craters, split it using electricity generated by solar panels in nearby sunlit ridges, liquefy the gases, and store them for departing spacecraft. Mars missions, asteroid missions, voyages to the outer planets, all of them could refuel at the moon before departing. The moon would become a fueling station at the lip of Earth's gravity well, the first service stop on the road to the rest of the solar system. The calculations engineers have run are genuinely encouraging. The problem is that the ice needs to be accessible, concentrated enough to mine economically, and located near terrain that receives adequate starlight for power generation. Here is where the story takes a troubling turn. The exact locations, depths, and concentrations of polar ice remain poorly understood. Scientists know water is there. The Lunar Crater Observation and Sensing Satellite mission confirmed it in 2009 by crashing a rocket booster into Cabeus Crater and analyzing the plume that rose from the impact. But knowing ice exists and knowing where to send a drill are very different things. The Volatiles Investigating Polar Exploration rover was designed to bridge that gap. A mobile laboratory built by the National Aeronautics and Space Administration. It was intended to drive across the lunar South Pole, measure ice concentrations, sample the regolith, and map the deposits in enough detail to plan a mining operation. It was cancelled in 2024 before it ever flew. The reasoning was bureaucratic. The consequences were enormous. Humanity surrendered its best near-term tool for understanding the most strategically valuable resource in the inner solar system. As of early 2026, the confirmed ice prospecting missions in the pipeline belong to other nations. China plans a small hopper aboard the Chang'e 7 spacecraft. A joint Japanese-Indian probe is in development. The United States, which confirmed that lunar water exists, appears set to watch other countries map its distribution first. Meanwhile, new research suggests the permanently shadowed regions are younger than previously assumed. Some craters may have only been in continuous shadow for around 1.8 billion years, which means the cold traps have had less time to accumulate ice than older models predicted. Deposits could be shallower and more diffuse than hoped. The most strategically valuable terrain in the solar system is still waiting to be properly surveyed. What comes next will depend on what we find there, and what we find there might already surprise us, because the moon has been hiding things in the dark for a very long time. Point a modest telescope at the moon on a clear night and find the dark western ocean called Oceanus Procellarum. Look carefully near its southern edge, and you will see something that should not be there. A bright, swirling curl of light, serpentine and luminous, draped across the dark basalt like paint brushed by a giant hand. It follows no mountain ridge, it follows no crater rim. It floats on the surface without topographic explanation, several hundred kilometers across, glowing inexplicably against the darker plains around it. This is Rhyna Gamma. Astronomers have been staring at it since the 17th century and still cannot fully explain it. Rhyna Gamma is the most famous of approximately 50 known lunar swirls scattered across the moon's surface. Some appear on the near side, some appear on the far side. Some are enormous, stretching hundreds of kilometers. Others are compact knots. All of them share two characteristics. They are brighter than the surrounding terrain, and they appear in regions with unusually strong magnetic signatures buried in the crust. That connection is the first clue, but it raises more questions than it answers. The moon has no global magnetic field today. That field died billions of years ago as the core cooled, and the internal convection that generated it gradually ceased. Yet, in certain patches of crust, ancient magnetism persists. The rock remembers a time when the moon was a different world. These localized fields are weak by Earth standards, amounting to only a fraction of what a compass needle responds to here. But they are strong enough to do something remarkable. The charged particles streaming constantly from our star, the stream scientists call the solar wind, normally bombard the unprotected lunar surface without interruption. Over hundreds of millions of years, that bombardment darkens and chemically alters the topmost layer of rock through a process called space weathering. The moon's dark plains have been fully weathered, beaten dark by billions of years of particle exposure. But where a crustal magnetic field deflects that stream, the surface stays protected, bright, unweathered. A ghost of what the moon once looked like before the solar wind had its way with it. That is what Rhyna Gamma is. A region of the surface shielded by a buried magnetic anomaly, preserved in its original brightness while everything around it darkened. The swirls are not artwork, they are fossils of a magnetic field that no longer exists. But this explanation only pushes the mystery one level deeper. If the swirls reveal buried magnetic anomalies, what created those anomalies in those specific locations? Why Rhyna Gamma and not the vast plains surrounding it? Why does the magnetic signature form such a precise and elegant ellipse, floating in a sea of material that carries no equivalent signal? Scientists have proposed a buried impact melt sheet, cooled in the presence of the ancient dynamo, as one candidate. Others suggest the structure is too uniform, too geometrically clean, to have come from a chaotic impact process. Whatever is generating the field down there, it is doing so with a regularity that implies shape and structure, not randomness. Three competing theories have battled for decades over the broader question. One involves the chaos of ancient giant impacts, sending shockwaves through the moon's interior. Another involves comets striking the surface and imprinting magnetic signatures through their plasma clouds. The third involves something buried far below, something that has never been directly observed. And one of those theories just received its strongest experimental support yet. The moon died magnetically. That much is agreed. Sometime between 1.5 billion and 3 billion years ago, the convection currents in the moon's molten outer core slowed and stopped, the global dynamo collapsed, and the magnetic field that had wrapped the entire world faded to nothing. Without that protective envelope, the solar wind reached the surface unimpeded, except in the swirl regions. Where the ancient crust retained pockets of remnant magnetism, something remarkable happens at small scale. The local magnetic field rises from the rock and forms a miniature version of the protective structure that Earth maintains globally. Scientists call these features mini-magnetospheres. They are tiny by planetary standards, extending only kilometers above the surface rather than tens of thousands. But they are sufficient to redirect the incoming particle stream, creating a shield above the bright terrain below. Think of it like an umbrella in a rainstorm, but the rain is a constant invisible current of charged particles traveling at 400 kilometers per second, and the umbrella is made of magnetic field lines anchored to buried magnetized rock. The swirls are the dry patches. Everything around them is soaked. This explanation is confirmed as far as it goes. The correlation between swirls and magnetic anomalies is not in dispute. The deflection mechanism is supported by measurements. What remains genuinely mysterious is how the magnetic anomalies formed in such specific locations, and why the crust there is magnetized so strongly while neighboring regions retain almost nothing. 3 hypotheses compete. The first suggests that giant impacts create focused shock waves that converge on the exact opposite side of the Moon. When a major basin-forming collision occurred on the near side, the energy channeled through the interior and concentrated at the antipodal point, magnetizing the crust there as it passed through the then active global field. Several swirls do sit opposite major impact basins, and this correlation is real. The second hypothesis involves comets. A comet nucleus striking the surface carries a plasma cloud in its coma, and that plasma, interacting with the ancient lunar dynamo, could have imprinted magnetic signatures in the surrounding rock. Rhina Gamma has been cited as a candidate for this origin, with researchers identifying a possible impact site nearby. The third hypothesis is newer, more unusual, and supported by laboratory work that few scientists had considered before. Something buried in the crust might be generating the anomaly from below. Magma that rose and cooled underground, never breaking the surface, locking in the orientation of the ancient magnetic field as it solidified. Hidden intrusions, invisible from above, detectable only through the magnetic shadow they cast on the brightness of the terrain overhead. Each of these 3 explanations fits some swirls better than others. The antipodal impact theory accounts for swirls at predictable locations on the opposite side of the Moon from known basins. The comet hypothesis explains isolated swirls with no obvious structural connection to anything else. The buried magma theory works wherever the surface shows no crater, no scar, no visible explanation at all. None of these theories covers every case, and some swirls remain completely resistant to any of the 3. In 2024, a research team ran the experiments to test whether the buried magma explanation was physically possible. What they found will change the way scientists look at every bright swirl on the Moon. In May 2024, researchers at Washington University in St. Louis published a study that gave the buried magma hypothesis its most compelling experimental support yet. The question they were testing was simple, and the answer was not. Can rock cool underground on the Moon and acquire a magnetic signature strong enough to produce the swirl patterns we observe on the surface? The answer, it turns out, is yes. Under the right conditions, spectacularly yes. The mineral at the center of the experiment is called ilmenite. It is abundant on the Moon, particularly in the titanium-rich basalts that cover much of the near side. Under surface conditions, ilmenite does not magnetize well, but the Washington University team showed that when ilmenite cools underground, under reducing chemical conditions with lower oxygen availability, it reacts to produce tiny grains of metallic iron scattered through the surrounding rock. Those iron grains are magnetically receptive in a way the original mineral is not. They ran the experiments under simulated lunar conditions, with temperatures and pressures matching different depths in the crust. The results were consistent. Subsurface cooling produced far stronger magnetic signatures than surface cooling under the same chemical conditions. Magma that never reached the surface, that rose partway and stopped, would be more magnetically powerful than lava that flowed openly and cooled in the open. This matters because it provides a mechanism that requires nothing extraordinary. The Moon had abundant magma. The Moon had a global magnetic field. Magma rising through the crust and stalling underground would have cooled slowly in the presence of that field, aligning its iron grains with the field's orientation, and then retained that alignment for billions of years after the field died. The result: an invisible buried structure radiating magnetic influence upward through the overlying rock, deflecting the solar wind, shielding the surface above it, preserving a bright patch of unweathered terrain in an otherwise darkened world. This is currently a well-supported theory. It has experimental backing, it fits the locations of known swirls, and it explains why many swirls have no corresponding surface feature. The magma never came out. It stopped below. And it has been quietly magnetizing its neighborhood ever since, invisible from above except for the brightness it protects. The implications extend beyond swirls. If the moon's crust is threaded with hidden magmatic intrusions, their locations and compositions record the entire history of lunar volcanic activity, including episodes that left no surface trace. The swirls are not just pretty features, they are a map of everything the moon pumped through its interior without letting the surface see. This hidden plumbing system could run for hundreds of kilometers through the crust, and some of those buried structures might be remarkably young by geological standards, much younger than scientists assumed when they declared the moon's volcanic age over. Consider what this means for every swirl scientists have catalogued. Each one is now a potential pointer toward an underground intrusion, a frozen river of magma that stalled before it could erupt. Each one is a data point in a map of the moon's interior history that no orbiting camera can see directly. Spacecraft that measure magnetic fields from orbit are, in a sense, X-raying the moon's hidden plumbing from above, and only now are scientists developing the tools to read those images. The evidence for recent volcanic activity in unexpected places came from somewhere no mission had ever gone before. On June 25, 2024, a small capsule streaked through the atmosphere over Inner Mongolia and landed on the steppe with roughly 4¼ pounds of rock inside it. That weight sounds modest. What it contained was not. Those 4 pounds represented the first material ever brought to Earth from the far side of the moon. China's Chang'e 6 mission had done what the entire history of space exploration had never managed. It had reached the moon's permanently hidden hemisphere, drilled into its ancient surface, and carried a piece of it home. All previous lunar samples, American and Soviet and Chinese alike, had come from the near side, the hemisphere facing Earth. The hemisphere covered in dark volcanic plains, rich in radioactive heat-generating elements, warm and geologically busy by lunar standards. Scientists had studied those samples for decades and built their entire model of lunar history around what they found. That model was about to be revised in ways nobody fully anticipated. The Chang'e 6 spacecraft had landed in the Apollo basin, a smaller crater sitting inside the vast South Pole Aitken structure on the far side. The choice was deliberate. The South Pole Aitken impact had stripped away much of the overlying crust in this region, potentially exposing material from deeper in the moon's interior than any near-side site could offer. If there was something fundamentally different about the far side, this was where samples would reveal it. The process of getting them home required extraordinary engineering. Because the far side faces permanently away from Earth, direct radio communication is impossible from the lunar surface there. China had launched a relay satellite called Queqiao-2 earlier in the year, specifically to bridge that gap, orbiting in a position that could see both the lander and Earth simultaneously, relaying commands and telemetry across the communication barrier that had made the far side inaccessible for so long. The samples arrived in laboratories around the world within weeks. What the analysis returned over the following months overturned assumptions that had stood for decades. The rock was volcanic, basalt, formed from magma that had risen through the crust and cooled at the surface. Scientists already knew the far side showed almost none of the dark volcanic plains that mark the near side surface so distinctively. No major maria, no obvious flood basalt fields. The far side appeared quieter, older, more heavily cratered, as though volcanic activity had ended there earlier and more completely. The samples said otherwise. 4 research groups, working simultaneously on different aspects of the material, arrived at the same conclusion through independent methods. Their findings appeared across multiple landmark papers in the same months, forming an overlapping case that was difficult to dismiss. Isotope analysis dated the basalt fragments to 2.83 billion years old. This was not ancient rock from the earliest moon. This was volcanic activity that had continued on the far side more than 1 billion years after many models predicted it should have stopped. The moon's hidden hemisphere had been erupting long after anyone expected it to. And the reason why pointed to something buried far below, something the South Pole Aitken impact had set in motion 4 billion years before the lava ever reached the surface. 2.83 billion years. That number is the center of one of the most important lunar discoveries of the decade, and it demands explanation. The far side of the moon does not look like a world that was erupting 2.5 billion years ago. Its surface is pale, cratered, dominated by ancient highlands. The dark volcanic plains that cover about 1/3 of the near side are largely absent. If you mapped the moon's volcanic activity purely from surface appearance, you would conclude the far side went cold much earlier than the near side, probably dying volcanically sometime around 3 to 4 billion years ago, when internal heat had dissipated too far to drive eruptions through the thicker far side crust. The Chang'e 6 basalts contradict this conclusion directly. Isotope dating is one of the most reliable tools in planetary science, reading the decay of radioactive elements like a clock that has been running since the rock first solidified. The clock in these samples read 2.83 billion years, confirmed volcanic activity. On the far side, younger than vast stretches of the near-side volcanic record. How is this possible? The answer involves the wound that never healed. When the object that created the South Pole Aitken Basin struck the far side 4.25 billion years ago, it did not simply scar the surface. The collision excavated material to depths of dozens of kilometers, thinning the crust in the region dramatically. The crust beneath the Apollo Basin, where Chang'e 6 landed, is significantly thinner than the far side average. Thin crust is easier to penetrate. Magma rising from depth needs to push through less overlying rock to reach the surface. The same internal heat that was insufficient to drive eruptions through a thick far side crust could push through the thinned floor of the South Pole Aitken structure without difficulty. The impact that should have ended everything in its path instead opened a pathway. The wound became a conduit. 4 billion years after the collision, the damage it caused was still enabling the far side to bleed. There is something else in the chemical record that adds another layer to this story. The Chang'e 6 basalts formed from magma with almost no detectable concentration of the radioactive elements that power the near side's ongoing volcanism. No potassium, no rare earth elements, no phosphorus to speak of. The far side mantle that fed these eruptions was chemically depleted, stripped of the materials that generate heat through radioactive decay, yet it still erupted. The implication is that the far side crust was so thin in this region that even a depleted, cooler mantle had enough energy to produce eruptions. The geological fingerprint left by the ancient impact was the critical factor, not the overall heat of the moon's interior. A 4 billion year old scar created conditions that produced eruptions 2 billion years later. The moon's history does not run in a straight line. It echoes, and there may be even more recent activity than anyone has dared to suggest. The youngest volcanic features identified anywhere on the moon, small irregular mounds called irregular mare patches, have been estimated at less than 100 million years old. If the South Pole Aitken impact could sustain a volcanic conduit for over 2 billion years, the possibility that some of these younger features sit above still active pathways cannot be ruled out. Scientists describe this possibility as speculative. The geologic record describes it as precedented. For decades, scientists knew the moon was lopsided, but they could describe the asymmetry only in surface terms. The near side has volcanic plains. The far side has highlands. The near side is lower in elevation on average. The far side is higher. The near side's crust is thinner. The far side's crust is thicker. What they could not confirm was whether this asymmetry extended deep into the interior, all the way down through the mantle to the core. Some models suggested the surface differences were a shallow inheritance from ancient events that had not penetrated far. The moon might look lopsided on the outside while being perfectly uniform below, The Chang'e 6 basalt samples ended that debate. A team from University College London and Peking University analyzed the chemical composition of the minerals in the farside rocks to determine the temperature at which the magma had originally formed. This technique works because different minerals crystallize at specific temperatures, and their ratios in the final rock encode the conditions deep in the mantle where the melt originated. The answer came back at approximately 1100 degrees Celsius. On the near side, basalt lavas of similar age formed from magma running roughly 100 degrees hotter. That gap persists throughout the entire volcanic history examined. Lavas from the same era, across the same billion-year window, consistently formed from cooler sources on the far side than on the near side. 100 degrees does not sound like much. On planetary scales, it is enormous. It represents a sustained, fundamental temperature difference in the mantle stretching from billions of years ago to the present. The moon's interior is warmer on one side than the other, and has been for almost its entire history. This asymmetry was created early. Scientists believe the culprit is an event called the lunar mantle overturn. When the moon's magma ocean cooled and crystallized about 4.5 billion years ago, a dense layer of minerals, rich in titanium and heat-generating radioactive elements, formed near the top of the mantle. This layer was heavier than the rock beneath it, gravitationally unstable. It sank, but it did not sink uniformly. Physical evidence published in 2024 using gravity recovery and interior laboratory data suggests the overturn deposited the heat-generating material preferentially on the near side, concentrating radioactive energy there and leaving the far side mantle cold and depleted. Every difference between the two hemispheres, every crater count and volcanic plane and magnetic anomaly traces back to that ancient redistribution of material in the deep interior. The moon chose sides 4.5 billion years ago. It has kept them ever since. In May 2025, a separate analysis of the moon's tidal behavior, published in Nature, provided independent confirmation. Scientists measured how much the moon's near side flexes under Earth's gravitational pull compared to the far side. The near side flexes measurably more. That difference in flexibility directly reflects a difference in internal temperature, because warmer rock deforms more easily than cold rock. The sample evidence and the tidal evidence, gathered through completely different methods, pointed to the same conclusion. The moon's lopsidedness is not a surface illusion. It goes all the way down. But there was one more surprise hiding in the Chang'e 6 samples. A surprise that rewrote the timeline of one of the moon's most important features and pointed toward a deep interior that was far more dynamic, far more restless than its quiet face suggested. There is a way to read a rock's memory. When magma cools and solidifies in the presence of a magnetic field, the magnetic minerals inside align themselves with that field, like compass needles frozen in place. The rock then carries the direction and approximate intensity of whatever field surrounded it at the moment of crystallization, preserved for billions of years unless something heats the rock again and erases the record. Planetary scientists call this paleomagnetism. It is one of the most powerful tools available for reading the history of worlds that no longer exist as they once were. When researchers measured the paleomagnetic signatures in the Chang'e 6 basalts, they expected a straightforward story. The moon's global magnetic field should have been steadily weakening by 2.83 billion years ago, the dynamo gradually running down as the core cooled and internal convection slowed. The rocks should carry a weak signal, a faint echo of a dying field. Instead, the signal was stronger than expected. At 2.83 billion years ago, the lunar magnetic field appears to have rebounded, intensities higher than models of a simple declining dynamo predicted. The field had fluctuated rather than declining smoothly. It had weakened at some point earlier, then partially recovered, then ultimately faded to extinction. This is confirmed by the sample measurements. The interpretation of why it happened remains a matter of active scientific debate. One possibility involves a mechanical stirring mechanism. As the moon's inner core solidified and grew over billions of years, the release of latent heat and the chemical buoyancy of the remaining liquid outer core could have driven renewed convection, temporarily reinvigorating the dynamo. Earth's magnetic field is sustained by a similar process today, though in a much larger and more energetic form. Another possibility involves the Moon's orbital dynamics. As the Moon gradually receded from Earth over billions of years, tidal forces shifted, changing the pattern of internal deformation. Tidal flexing of the interior can drive fluid motion in the core. At certain distances and orbital configurations, that motion might have been sufficient to pump the dynamo back up to unexpected strengths. Either way, the implication is significant. A world with a magnetic field is a world with a molten, actively convecting interior. The Moon was genuinely alive inside, dynamically producing and sustaining a global magnetic field for far longer than a simple cooling model would predict. The field pulsed, it fluctuated, it refused to die quietly. And when it finally did die, it left its fingerprints everywhere, in the paleomagnetic records of rocks scattered across both hemispheres, in the swirls glowing bright on the surface above buried magnetized intrusions, in the complicated magnetic geography of a world that once shielded itself from the stars. What this tells us is that every rock on the Moon is, in some sense, an archive of forces that no longer operate. The core that drove the dynamo is now still, the convection that stirred it has ceased. But the record of every magnetic fluctuation, every pulse and rebound over billions of years, survives in the rocks that cooled during those episodes. Scientists are only beginning to read that archive systematically. The picture that emerges from every line of evidence is not the dead world that textbooks described. Something far stranger has been hiding under that familiar, placid face. And to understand what, you have to step back and take in everything at once. Stand far enough back from the Moon, and a single coherent story emerges from all the separate discoveries. It is a story of violence and consequence, of a world shaped by one catastrophic event 4 billion years ago that is still producing reverberations today. 4.25 billion years ago, a differentiated proto-planet struck the young Moon on its far side. The collision was unimaginably energetic. It excavated a crater 2,500 kilometers across. It stripped the crust to almost nothing across a quarter of the lunar surface. It may have injected the metallic core of the impactor deep into the mantle, where it has remained suspended ever since. 2 quintillion kilograms of iron and nickel locked in place by the rigidity of the cold far side mantle, still dragging the basin floor downward by more than half a mile. The impact left the Moon fundamentally split. The far side crust thickened in response to the redistribution of material. The near side accumulated radioactive heat-generating elements when the unstable upper mantle overturned, sinking and depositing its enriched cargo preferentially beneath the hemisphere facing Earth. One side grew warm, the other grew cold, and they stayed that way for the entirety of geological time. From that moment, everything followed. The warm near side drove vigorous volcanic activity that flooded its surface with dark basalt. The radioactive elements powered a dynamo that generated a global magnetic field, alive and fluctuating for at least 2 billion years. When the field finally died, the ancient magnetism it left in certain portions of the crust created mini-shields that protect the surface above them still, visible today as the bright swirling patterns that puzzled astronomers for centuries. The cold far side went quieter, but never entirely silent. The thinned crust beneath the South Pole Aitken scar allowed magma to punch through, even from a depleted mantle, generating eruptions 2.83 billion years ago that no surface feature would predict. The impact that should have killed the far side geologically instead gave it a conduit that kept it intermittently alive. Moonquakes continue to shake the interior as the whole body shrinks. The crust cracks and thrusts, and slips along faults that were active 90 million years ago and may still be generating tremors today. Underground caves, formed by ancient lava tubes, extend through the volcanic plains, stable at 17 degrees Celsius, while the surface above swings 300 degrees between lunar day and night. At the poles, The geometry of the moon's minimal axial tilt creates perpetual darkness in crater floors, where frozen water has accumulated over billions of years, delivered by comets and preserved by cold, waiting to be used. Every one of these features is connected. Every one traces to the same origin wound. The moon is not a passive rock. It is an active geological system with a memory stretching back to the earliest chapter of the solar system. Still settling, still contracting, still occasionally surprising the scientists who watch it. No seismometer currently operates on the lunar surface. No seismometer has operated there since 1977. The entire picture assembled here comes from orbital measurements, return samples, and archived data. Imagine what a global seismic network on the far side would reveal. Imagine drills at the poles, rovers in the lava tubes, instruments lowered into caves that have been sealed since the last eruption billions of years ago. The most unsettling realization of all is this: we have barely begun to read what the moon is telling us. Here is the honest answer to the question this documentary has been building toward. Nobody knows, not completely, not yet. Every layer of the moon carries a different secret, and scientists have confirmed some of them, theorized about others, and can only guess at a few. Start at the top and work downward. Near the surface, in the polar shadows, lies frozen water. This is confirmed. The molecules are there, trapped at temperatures cold enough to preserve them across billions of years. Exactly how much water, how concentrated, how accessible to future extraction, those questions remain genuinely open. The rover designed to answer them was cancelled before it ever flew. Below the surface of the volcanic plains lie cave systems, remnants of ancient lava tubes formed when rivers of molten rock drained away and left hollow tunnels behind them. These are now confirmed to exist. One was detected beneath the Sea of Tranquility in 2024, a void at least 45 meters wide, stable, shielded, the size of a city block underground. Almost certainly, this cave is one skylight into a much larger system that extends for kilometers in multiple directions, large enough to house entire settlements in natural radiation-shielded enclosures. How far that system extends is unknown. Deeper still, in the upper mantle beneath the South Pole Aitken basin, lies the anomaly, a mass of at least 2 quintillion kilograms of dense material suspended hundreds of kilometers down, pulling the landscape above it lower than it should be. Whether this mass is the dispersed metallic core of the ancient impactor, or a concentration of dense oxides from the moon's original cooling, remains genuinely unresolved. Both hypotheses are scientifically defensible. Neither has been confirmed. The material itself will never be sampled by any technology that currently exists or is currently planned. And woven through all of it, in the rock and the seismic vibrations and the magnetic signatures, is evidence of a world still evolving. A world with a thermally split interior, one side warm and enriched, the other cold and depleted. A world that shakes and contracts, and occasionally cracks open a new fault. A world whose dynamo pulsed and fluctuated for billions of years before dying, leaving its memory in magnetized rock. A world that was volcanically active longer, on both sides, than every model built before 2024 predicted. The terrifying thing is not any single discovery in isolation. It is the accumulated weight of realizing how wrong our comfortable assumptions were and how recently we began to correct them. The seismometers that first hinted at a living interior were turned off in 1977. The gravity mission that revealed the mass anomaly flew for 1 year, and then its spacecraft were crashed into the surface. The far side samples that rewrote lunar history weigh less than 5 pounds. The cave confirmation came from radar data collected in 2010 and reanalyzed 14 years later. Every breakthrough has come from data that already existed, reinterpreted with better tools and better questions. Imagine what dedicated new instruments would find. The moon is not a museum. It is a library we have been reading by candlelight. Beneath that silent, familiar face, something has been waiting 4 billion years to be understood. We are only now learning how to look, and what we find next will not just reshape lunar science. It will reshape our understanding of how every rocky world in the solar system was born, survived, and hid its secrets from the species that thought it knew them. We are just getting started.